By now you've recognized that Chapter 8 is kind of about integration techniques, whereas we did a lot of stuff with applications of physics in Chapter 7. Now we're learning more and more ways to find antiderivatives. And that's going to continue with something called partial fractions. We'll see and use something like that in problems like number 6, 2 over 9x squared minus 1 dx. Now the thing about 9x squared minus 1 is that we can factor that. That's really the product of two so-called linear terms. It's the difference of squares, factorization. Hopefully you're familiar with that. And now what's true about this is that this kind of decomposition really comes from adding together two fractions. Something over 3x minus 1 and something else over 3x plus 1. So we've got a linear term in the denominator for each of these terms here. The goal for us is going to be to figure out, well, what are the values of a and b that make this true? How do they equal? So there's a couple ways you can solve this, and I think at least in this first one I'll show you both. You do kind of need to know both, although we're not always going to use both. The first thing I'll do, either way I solve this, is I'm going to multiply both sides by the lowest common denominator. So the lowest common denominator is really this term over here. It's your 3x minus 1 times 3x plus 1. So 3x minus 1 times 3x plus 1. 3x minus 1 times 3x plus 1. And I'm hoping that it's very clear that on the left-hand side we get some marvelous cancellation, right? That just leaves us with a 2. On the right-hand side, we're also getting some more cancellation. Let's just kind of do it by eyeballing it. 3x minus 1 will cancel with a 3x minus 1. It leaves me a times 3x plus 1. Plus b times what? 3x minus 1. Now there's a couple ways that we can solve this. We need to eventually figure out what a and b equal. So the one way is to kind of equate coefficients. And how does that work? Well, this is 3ax plus a plus 3bx minus b. And let me put the x terms together. So that would be this one and this one. And then what's left is the constant terms. So that's these two. So I get 2 equals 3ax plus 3bx plus a minus b. Now one last thing I'll take care of, and that is I'm going to factor out the x, the common factor here. So that's going to be 3a plus 3b times x plus a minus b. Now, does it hurt things if I put 2 plus 0x? Am I okay there? I think I'm okay, because 0 times anything is 0. But what this does for me is it sets up a system of equations. The coefficient of x here has to equal the coefficient of x here. And the coefficient of the constant here equals the constant here. So I've got two unknowns, a and b, and I'll get two equations. That's why I needed to set up this 0x here. My two equations look like this. 0 equals 3a plus 3b. What's the other equation? Anyone tell me? Two equals a minus b. And you can solve this system of equations any way you want. All right? It's pretty basic one. You could use the addition method, you can use the substitution method. You can even do it on your graphing calculator. Doesn't matter to me. Now, setting up a system of equations, yeah, it works. It's not terribly fun. So let me show you a different approach to solving for A and B. It's going to be a little bit faster. But you're okay with where we're going here? A is going to equal 1, and B is going to equal -1 when you finish solving. So we'll go back and rewrite this integral in a minute. The part that I need your input on is, are you okay with how we found our system of equations? Okay. There's a different way that we can solve for A and B. Let's go back to this line right here. Right there. So A equals, excuse me, 2 equals A times 3x plus 1 plus B times 3x minus 1. And let's choose a couple clever values for x. And what do I mean by that? Well, let's say, for instance, let's set x equal to -1/3. Do you see what's special about -1/3? If I put in -1/3 here for x, what's going to happen to that binomial term? It's going to be 0, right? Because 3 times -1/3 is going to be -1, plus 1 is going to be 0. So this equation becomes 2 equals A times 0 plus B times, well, we'll have to clean things up here. 3 times -1/3 minus 1. It's going to be, well, that's just 0, so I'll just ignore that. B times -1 minus 1. Or better yet, 2 equals -2b. Cool. So I get -1 for b. Nice. Let's go up and solve for A. Now I used x equals -1/3 because that canceled out the A, and I was able to solve for B. Now I want to cancel out the B and solve for A. So what value of A, or what value of x can I use to cancel out the B? Yeah, +1/3. Set x equal to 1/3. 1/3 times 3 is 1. 1 minus 1 is 0. So 2 equals A times 3 times 1/3 plus 1. And I know this is going to be 0, but let me at least just put it in so you can see it if you're interested. 3 times 1/3 minus 1 is 0. This whole term disappears. 2 equals 2a, so 1 equals a. So that was the other thing that I needed. I needed A and B. So generally speaking, I think this, I've heard it called the cover-up method. What we did here is a little easier. You don't have to set up a system of equations. But even if you did, you'll get the same solutions, 1 and -1. Let's go back to the top here. I ended up with 1 for A and -1 for B. So I can rewrite this as an equivalent problem. 1 over 3x minus 1 plus -1 over 3x plus 1 dx. I went through a lot of effort to get there. Did it do me any good? Can I integrate this whereas I couldn't integrate that? Yeah, what am I going to use to integrate these? Natural log. So you could split it up if you'd like. That's the integral of dx over 3x minus 1 minus the integral of dx over 3x plus 1. Maybe you need to use a U substitution. Kind of depends on you. If you did, you're going to find that you need a factor of 1/3. We'll end up with 1/3 the ln of 3x minus 1 minus 1/3 the ln of 3x plus 1 plus your constant. If you look up your answer in the back of the book, you might not see this. Might not look quite like that. The book has a tendency to play around with your properties of logarithms. So what would those be? Well, we could factor out the 1/3. 1/3 times the ln of 3x minus 1 minus the ln of 3x plus 1 plus your constant. And here they're going to use the quotient rule. So it's going to be 1/3 the ln of 3x minus 1 over 3x plus 1. So they're just using the quotient rule in this last part. For me, the important part is not the fancy stuff at the end. It's the decomposition into the two partial fractions that allows you to integrate it with the natural log. Liam, looking good on that one? All right. Overall, are we okay with this one? I mean, the hard part is coming up with the solution for A and B. Now, what's going to happen is we're going to run into different circumstances. We'll start out with what's called the distinct linear case, where you've got, two different factors here. But what if one of these was squared or cubed or something like that? What if instead of having a linear factor, I had a squared term like x squared plus 4? Then what happens? So you're going to get different cases, but all of them are going to be solved by decomposing it into parts. Let's try problem number 12. The integral of x plus 2 over x squared plus 5x. dx. Now, it's probably helpful as we work with this to think of this in its factored form. How can I factor x squared plus 5x? Thank you. X times x plus 5. Just factor out the GCF. Now, for each one of these linear terms, we're going to put a term in the denominator. A over x and b over x plus 5. I think you're going to find this one works out a little bit friendlier. As with the last one, I'll multiply both sides through by this denominator, x times x plus 5. So x times x plus 5. Try and write down for yourself what equation is going to be left after you distribute this term. What am I going to have? Delane, what equation am I going to get when I distribute that? What's left? Yeah, plus b times x. Now here's where that trick that I showed you in the last one is going to help out. So Ronnie, let's try and pick a couple clever values to help us solve here for x. So what's a value for x on the right hand side that would work out pretty good? Set x equal to Yeah, negative 5 looks like a winner. So that'd be negative 5 plus 2 equals a times negative 5 plus 5 plus b times negative 5. So this term wipes out altogether. And we're left with negative 3 equals negative 5b. Divide both sides by 5. I get 3/5 for b. Hey, and that worked out pretty good. Now that gives me b. Thanks, Ronnie. What am I going to do to solve for a? Vicky, suggestions? What could I set x equal to? One more time. 0, good. Set x equal to 0. So I get 0 plus 2 equals a plus 0 plus 5 plus b times 0. And as before, that disappears. That's just a 0 now. 2 equals 5a. So 2/5 is a. That's nice. That worked out really nice. So what I can do is I can replace this function by the addition of these two functions. And that should integrate really easily. So this integral, x plus 2 over x times x plus 5 dx, is going to decompose into the integral of 2/5 over x plus 3/5 over x plus 5 dx. And that's nice. This is going to work out pretty easily. Andrew, what are these integrals going to be? I get 2/5 times what? Some help? Yeah. So it's 2/5 ln of x plus 3/5 ln of x plus 5 plus your constant. And again, you can play with this a little bit and pretty it up, clean it up a little bit. I'm not so worried about that much as I am you getting this far, getting the partial fraction decomposition. How's number 12? Looking a little bit better? Okay. If it's not, please help everybody out, yourself, myself, and your classmates, by asking a question. I mean, that's why they pay me the big bucks. So help me out if you would. All right. No one wants to be the first to ask a question. Does anyone want to be the second to ask a question? Yeah, I mean it's just a constant, right? So I took that out of the integral and then integrated. Now, if you needed to check your answer, I mean, one of the things that I could see that the book might do would be factor out the 1/5, and then that leaves behind 2 ln of x plus 3 ln of x plus 5 plus a constant. And then these terms come up as exponents. So it's 1/5 ln of x squared. I don't need the absolute value anymore because it's necessarily going to be positive, plus ln of x plus 5 to the third power. And then finally, 1/5 ln of x squared x plus 5 cubed, just using the product rule here. So there really is a fair amount more that you could do. I'm not going to worry about that so much. Yes, we'll get there. We'll get there. Yeah. So the question is, can you expand this process to have a cubic function in the denominator? And the answer is yes. In fact, tell you what, let me change up the order and how I was going to cover this, and let's do that with problem number 16. Now, one kind of heads up about something we're going to see in problem number 16. Problem number 16 is going to be a case where you have a repeated linear factor. So let's take a quick look at one of the examples in the book. So this denominator factored as x times x plus 1 squared. When you set this one up, you've got the linear factor here for the x, and then one for the x plus 1, and then another one for the x plus 1 squared. Now, if this was a cubed, then I'd have yet another factor, d over x plus 1 cubed, if that was factored. So what you need is one of these terms for each power, starting with 1 up to the exponent, for these repeated linear factors. So that is something that has, a higher power other than 1. Let's look back then at problem number 16. So right here. Let me copy that down onto my sheet for us. So probably want to zoom out a little bit. The integral of 8x divided by x cubed plus x squared minus x minus 1 dx. Now this one looks really intimidating. It's like, well, wait a minute. Hey, come on. Professor guy, you didn't give it to us factored. What's up with that? Well, I guess you got to factor it, right? So let's start out by figuring out how this factors. And I'll do that off to the side here. X cubed plus x squared minus x minus 1. So it's not a trinomial. It's a quadrinomial if you want. It's a polynomial with 4 terms. But when you have 4 terms, there's something that I always suggest. And that is factor by grouping, factor in pairs. So let's take a look at the first pair. What can I pull out of that first pair? An x squared. And that leaves behind x plus 1. Is there anything I factor out of the second pair? Negative 1. And that also leaves behind an x plus 1. That's good news. These two terms match. So what that allows me to do is to factor out the x plus 1. What gets left behind after I factor out the x plus 1? X squared minus 1. And x squared minus 1 also factors. It's the problem that never stops, right? How does x squared minus 1 factor? X minus 1, x plus 1. And finally, x plus 1 times x plus 1 is x plus 1 squared. So x plus 1 squared times x minus 1. Cool. Now we can start our problem. After 5 minutes, right? All right. Well, let's take a look at what that does for us then. I can rewrite this as 8x over x plus 1 squared times x minus 1. Let's see if we can't figure out the things that we're going to need on the right-hand side. It's going to be a total of 3 of them. Let me start this way. A over x minus 1. B over x plus 1. Go ahead. C over... Perfect. C over x plus 1 squared. So, nice. So what was that? Yeah. Now, it may turn out that A, B, or C could be negative. So one of these could be negative. We're just setting up positive to start with. All right, but could turn out that one of these is negative. Could turn out that one of them is 0. All right. They shouldn't all be 0, but one of them could be 0. As before, I'm going to multiply everything by the LCD. Kind of running out of room here, so the LCD is just the denominator of this, always. We'll get 8x equals A times what? X plus 1 squared plus B. Now B will cancel out one of those. So it's going to be x plus 1 times x minus 1 plus C times what? X minus 1. Now here we have to be a little bit more careful. If you're clever, we can avoid having to set up a huge system of equations. So let's see if we can't do that. Because I'd rather not solve this with a system of equations. Yes, sir? One on the top? I'm sorry, I couldn't quite hear, the train was going by. Why wasn't there an x plus 1? Well, because this term is squared, you have to have x plus 1 to the first power and x plus 1 to the second power. If this was a cubic term, I'd have a plus d over x plus 1 cubed, etc. It would keep on increasing with the exponent. You'd have a term for each power of this exponent. It's just the pattern of the partial fraction decomposition. Now, as we solve for this, sometimes one or more of these will turn out to be 0. I don't think that's going to be the case here, but I don't know yet. Just not sure I've answered your question, though. So
I think he's wondering why when you use the LCD, why the C doesn't have the x plus 1 with it as well.
Oh, you could, let's see. Well, when we multiply through by the LCD, that's going to cancel with that term in the LCD. So it's just going to leave you with C times x minus 1. It'll cancel out altogether. Right? Because this is your LCD. So everything gets multiplied. Here, let me see if I can't squeeze it in. So x plus 1 squared times x minus 1. X plus 1 squared times x minus 1. X plus 1 squared times x minus 1. And x plus 1 squared times x minus 1. So when I do that, I get everything here cancels with everything here. So I get 8x. I don't think there's any dispute about that. And then here, I get rid of the x minus 1. So that leaves me with a times x plus 1 squared. And then here, I get rid of one of these terms. So that will cancel with one of these. It leaves me with x plus 1 times x minus 1. And the last one, that whole term cancels, so it leaves me with c times x minus 1. Now, the order that you choose here doesn't matter. I could choose to order these denominators in any way, and I can choose to order these constants in any way. It's all going to come out the same in the end. Let's play our game again. We need to come up with some values of x that will help us solve for a, b, and c. All right, we'll start with -1. X equals -1. It's going to be 8 times -1. Now, if I put in a -1 here, which of these terms are going to drop out? I'll have a times 0 squared plus b times 0 times something else, doesn't really matter, right? Because it's still going to be 0. plus c times negative 1 minus 1. Yeah. So overall, I get negative 8 equals negative 2c, or 4 equals c. Yay. Let's grab that one. Well, I can play this game again. We chose x equal 1. That worked out good for the first one. What else can I choose for x? 0 I don't think is going to cancel out anything to the point. Positive 1. Let's choose x equal positive 1. So that gives me 8 times 1 equals a times 2 squared. What's going to happen to b and c if we choose x equal 1? b times 0 plus c times 0. In other words, both of those cancel. So we get 8 equals 4a, or 2 equals a. Now's where I got to get clever, though. There's no more easy values I can pick without doing something first to help finish solving for b.
You plug in the a and the 4?
Perfect. We know what a is, we know what c is. So if we plug in a and c, then we're free to pick one more value for x, and we'll be able to solve. But well done, Ted. Well done. So let's plug all those in. So this becomes 8x, and a was 2, equals 2 times x plus 1 squared, plus b times x plus 1 times x minus 1. And c was what, 4? Yeah, c was 4. So 4 times x minus 1. Now, this equation holds for any value of x. So the clever thing to do is to pick an easy value of x and then solve for b. There's two values that come to mind as being easy. I'd say x equals 0 and x equals 2. I think I like x equals 2 better because that makes this term 2 minus 1, which is going to be 1. X equals 0 works out pretty good too. You just got to be careful with the negative there. Okay, so 8x equals, what are we going to choose for x? You want to choose 2 or 0? 2? All right. 2 plus 1 squared plus b times 2 plus 1 times 2 minus 1 plus 4 times 2 minus 1. Oops. Should be 8 times 2 here. I need to plug it in here. So it gives me 16 equals 2 times 9, which is 18, plus b times 3 times 1, plus 4 times 1. Just simplifying this all out. 16 equals 18 plus 3b plus 4. 18 and 4 is 22. If I subtract 22 from both sides, I'll end up with negative 6 equals 3b. And finally, I get negative 2 for b. So that's the last of my coefficients. I think it's much more efficient to do it this way than it is to try and set up and solve a system of equations. You can set up and solve a system of equations. That'd be an equally decent way of doing it. I don't think you would enjoy solving a 3x3 system of equations to finish this one up and find a, b, and c. Remember, we still haven't done our integration. All we've done is we figured out the partial fraction decomposition. Let's put in a, b, and c into our partial fraction decomposition. So a was 2, b was -2, and c was -4. Let's put it in right here. That's going to equal, so this is going to equal the integral of 2 over x minus 1 plus -2 over x plus 1 and plus 4 over x plus 1 squared. So I'm just putting in the values for a, b, and c into there, and I get this integral. The nice thing is that I can integrate at least 2 of them pretty much directly. I mean, if this was Calc 1, I'd probably consider taking the time to do a u substitution, but I'm hoping that you can look at these and realize that, all right, du equals dx, let's just integrate it straightforward. 2 times what? ln of x minus 1 minus 2 times ln of x plus 1. Now this one we need to be a little bit more careful with. That's not a natural log. So let me take a peek at that one up here. I'll write that as 4 times x plus 1 to the -2nd. What's going to happen when I integrate this one? Power rule, right? -2 plus 1 is -1. Divide by that same exponent. So that's that last term. Add 1 to the exponent, divide by the same exponent. And that's essentially what you're going to do as long as this exponent is not -1. Because then you'd end up dividing by 0, and that's going to be a no-no. That's where you get your log term. How does this clean up? Thank you. -4 over x plus 1 plus your constant. Whew. So, Liam, I think you started this. You're like, well, what if we had a cubic one? Good question. Don't worry, we'll get you security to walk you out to your car. All right, that's a long one. Whew. Man, pass the oxygen bottle. All right, let me recap here, because that one was kind of a long one. And if along the way that you see something that you'd like me to slow down on, let me know. We started out by factoring that. The trick in this one was to factor by grouping. You're going to do that when you have 4 terms, so we factored out the first pair and the GCF from the second pair. We had a greatest common binomial that we factored out, which factored further down to this. That gave you the repeated linear factors case. This x plus 1 term was repeated, so I have it repeated here and here, to the first power and to the second power. You've got your a over x minus 1 term, and then these other ones. Multiplying through by the LCD gave us this equation right here. And it's this that helped us solve at least part of things right here. First we said x equal to 1, -1, then we said x equal to 1. That got us pretty far, right? You know, we were able to solve for C and for A, but then you run out of luck. There's no more things you can plug in without killing one, the other, or both. So Ted's suggestion was a really helpful one. It's like, okay, well, now that we know A and C, let's plug in those values and then use that to solve for B. So we did that here. Plugged in our values for A and C. Set x equal to 2. That allowed us to solve for B. The rest of it was just rewriting on our integrand and then integrating. That was the easy part. Integration was actually pretty straightforward once we got down to that form. Okay. There's a couple more cases that we got to discuss. Let's try problem number 18. The integral of 6x over x cubed minus 8 dx. Now the unfortunate part for us is that I think a lot of people will forget how to factor the denominator. So off to the side here, let me remind you of the difference of cubes factorization. It's always a binomial times a trinomial. Yeah, some people remember their correct acronym. A and a B, A squared, AB, B squared. A and a B, A squared, AB, B squared. So right now they look pretty identical. Where they're different is the signs involved. And to help you remember the signs, there's an acronym that I hear a few of you whispering. It's called SOAP. These first two signs are the same, so minus and minus. These next two signs are opposite, so minus and plus. And the last one is always positive, so that's a plus. Now try and use that down below to fill in those signs. Same, opposite, always positive. So with that, yeah, please. Minus, 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 plus, plus. No, that looks right. Same refers to these two. Yeah. All right. No, it's all right. I appreciate it. Appreciate it. So 6x dx, well, it's always going to be a binomial, so that's going to be my x minus 2. Those are the terms that I cubed to get that. And then the rest of this is going to be x times x gives me an x squared. 2 times 2 gives me a 4. And the middle term is the product of those two terms. So 2 and an x. How about the signs that go in here? What signs go in here? Both positive. What do you think about x squared plus 2x plus 4? Am I going to get any farther with that one? No. So this is yet another case. Let's think about the cases we had so far. We started out with the really nice case, the distinct linear factors case, where you had an x and an x plus 5. All right. Then we had the repeated linear factors case, where you had an x plus 1 squared. Now you've got the next case, which is a quadratic, a prime quadratic. That term in the denominator can't factor anymore. So it's a different setup. 6x over x minus 2 times x squared plus 2x plus 4. 2x plus 4. So as usual, you're going to have a representative for the linear term. It's going to be a over x minus 2. But since this term won't factor, it's just going to be a quadratic term in the denominator. X squared plus 2x plus 4. The relationship between numerator and denominator is that the numerator is 1 less of degree than the denominator. So if this is to the first power, this is a constant, or to the 0 power. If this is a squared, this has to be a linear term, right? And so a general linear term would be bx plus c. So So that's your partial fraction decomposition for this one. All right, let me move over to another sheet here. But it's, like I said, it's another case here. They actually can get kind of messy. If you had a squared linear term, then we'd have to have this term and then this term squared. I'm going to draw the line here. This is as messy as it's going to get for us. I'm not going to give you something that's really totally crazy and off the wall. So let's see. A over x minus 2 plus bx plus c over x squared plus 2x plus 4. 6x over x minus 2 times the quadratic. As before with all these, we're going to multiply both sides by the lowest common denominator. And let me kind of squeeze that in next to everything here. X minus 2 times x squared plus 2x plus 4. X minus 2 times x squared plus 2x plus 4. And x minus 2 times x squared plus 2x plus 4. So each term is going to get multiplied by that denominator. Now, very nicely, on the left-hand side, everything cancels. You're just left with 6x. On the right-hand side, again, you're going to get some cancellation. The x minus 2 term is going to cancel from the right-hand side. So let's do that. That's going to leave me with a times x squared plus 2x plus 4 plus bx plus c times x squared, or actually not that. What's bx plus c going to multiply by? Yeah, x minus 2. Now, you can play your little cover-up game, but it's only going to get you so far. You could choose x equal 2, and that would allow you to solve for a. You'd have to plug back in a, and then solve for b, and then plug back in, or solve for c, and then plug back in c, and solve. It'd be a lot of work. So let me review the other way that we had to solve these things and show you something that you might find convenient in your calculator, not only for this class, but for other classes. So let's distribute here, and I get 6x equals ax squared plus 2ax plus 4a. And over here, I'll FOIL. I'll get bx squared minus 2bx plus cx minus 2c. We're going to set up a system of equations, much like we did with the very, very first problem here. I'm going to write this as 0x squared plus 6x plus 0. Kind of foreshadowing what's coming. On the right-hand side, I've got both of these terms involve an x squared. So let's factor out the x squared and write that as a plus b times x squared. I've got some terms that involve an x. So it's going to be it's going to be 2a minus 2b plus c times x. And the last terms here are my constants. So I'll just kind of group those together. It's going to be plus 4a minus 2c. as before, we can set up a system of equations now. The first equation comes from here. Second equation comes from here. And the third equation comes from here. So my system of equations is this. 0 equals a plus b. What's the second equation? 6 equals, thank you, 2a minus 2b plus c. And finally, 0 equals 4a minus 2c. Now this probably wouldn't be all that bad, even if you had to solve it by hand. But let's assume that you've borrowed one of my calculators or that your calculator is nicely up to date. And you want to employ some technology here. So, this assumes that you have an up-to-date TI-84. Let's go to the Apps button. So, for the Apps button, go down to Simult 2. So for me, this is number 8. You can just type the number 8 or cursor down and press enter, either way. But you hit the second button, or no, you just hit the Apps button, which is right here next to the math key. You should get this. And let's select Simult 2. And it asks you, what do you want to do? You want to find the roots of a polynomial? No. I want to solve a simultaneous system of equations. So I'll select that one. I've got 3 equations and 3 unknowns. And then the rest of it, I think we're okay. So let's go to next. And it's going to ask me to input my coefficients. So the coefficients are 1 and then 1 again. What should I put in front of the z? 0, right? Because there's no, their x, y, and z is arb a, b, and c. So 0, and that equals 0. Let's do the next one. 2. Let's try it again. 2, and then negative 2. And then, what's the last one? What should I put here? 1. And that's going to equal 6. And finally, 4, 0, and negative 2 equals 0. I hit the Apps button, then Simult 2, and then the second one was System of Equations, Simult. I think I'm in good shape, so let's solve. There you go. 1, negative 1, 2. Like that one? Is that a good trick? Yes?
Sorry, I'm on the Simul solver mode. I don't know how to get to the next.
You just show me where you're at. Press the next button in the lower right corner. Should say next. Alright, so the bottom line that I needed from this, regardless of how I did this, I mean, there's nothing wrong with solving this in other ways, but we got a was equal to 1, b is equal to negative 1, and c is equal to 2. Yeah, you could set up these systems of equations and solve them, you know, on a calculator. Yeah, you don't have to do it with necessarily the cover-up method that we've done where you choose a value for x. So I've given you a lot of freedom in how you want to solve these things. Yeah. Okay, so let's go back to the integral. That means that our integral is going to break up to 1 over x minus 2 plus negative x plus 2 over x squared plus 2x plus 4 dx. Okay. This one's just a log. This one actually becomes quite a pain. I'm not going to kind of give you all this painful stuff on top of a really long problem like this. I don't like to test too many things in one problem. So I'm going to kind of limit that there. Yes, sir. B, I got -1. This is going to split up as a log. The actual trick in this one is to split this up so that you can do part of it with a du, and then the other part's going to be a arctan. Yeah, it becomes a real pain. In case you're curious, the final answer is the ln of x minus 2 minus 1/2 the ln of x squared minus 2x plus 4 plus square root of 3 times the arctan of x plus 3, or no, x plus 1 over the square root of 3 plus a constant. I don't want to spend another 10 minutes just to finish that part up. The important part that you see is how to split up something that has a prime quadratic in it. And by that I mean something that's a quadratic term that won't factor. You have to have that linear term up here to do that. Let's see, system.
So you plug in 1x, you make a 3 by
Yeah, so it's a 3 by 3. Basically regarding it as being plus 0c, and then you've got a 0b here. So the coefficients here are really the coefficients here. Let me see if I can't clean this up a little for you. Yeah, so I could put 0b minus 2c. All right, so now all the coefficients here should line up with the coefficients here. This is just the right-hand side. Okay? Yeah, then you just hit solve. Yes, sir. I'm not sure that it solves it necessarily with a determinant. There's literally a gazillion ways to solve these types of system equations, and what they do exactly, I'm sure, is proprietary. One of the ways that you can solve it, and of course for something this small, it'd be overkill, is something that you're actually familiar with from popular culture. Has anyone ever done those little scan something in? You have a little box of dots, a little square box. You scan it in and it takes you to a website. They're called QR codes. And one way that you can solve a system of equations, and I know there's got to be a connection, I never really pursued it, but it's just called the QR algorithm as a way you can solve a system of equations. So, but that's like squirrel hunting with a bazooka for something this small. All right. I think, I wouldn't mind doing one or two more here, but I don't know about you. I'm running out of gas. Let's do a break. I'll put in a couple extra problems at the start of class after the break. So I'll see you in 10 minutes.